Hi students, my name is Mr. Low. Today I'm going to share with you two common calculations that you'll come across in this topic called chemical energetics. Now the first calculation is from calorimetry. Now calorimetry is a direct method of measuring enthalpy change by measuring the initial temperature and the final temperature of the solution itself. Okay. Now to do this calorimetry calculation, there are two formulas I need to know. Number one, Q equals MC delta T. Now, what is Q? Q is the heat absorbed or evolved. So this is your Q. Now, in MC delta T, the most important alphabet is your M. Now, M is the mass of the solution in gram. Okay, it can also be the volume of the solution. Because in energetics, we assume that all solutions have a density of 1 gram per cm cube. So if your density is 1, your mass of solution is equal to the volume of the solution. Now, please take note, your M should never include the mass of the solid, because when your solid goes into the styrofoam cup, it will have totally dissolved. C is the specific heat capacity. It has a fixed value of 4.18 or 4.2, and your delta T is a change in temperature, in which we take T final minus T initial. Now, your delta T can be degrees Celsius or Kelvin. There is no need to convert degrees Celsius to Kelvin at all. Okay, so this is the first formula. Now the second formula, delta H is equals to minus Q over your N, where your Q we just found is minus empty delta T, okay, over your N. Now your N here stands for the number of moles of emitting reagent. It can also stand for the number of moles of water if you're talking about neutralization reaction. Now some school uses another alternative. They use delta H is equal to plus minus Q over N. Now, if your school does that, for endothermic reaction, you have to use the plus. For exothermic reaction, you have to use the minus. My formula, I just use minus, because my delta T is always TF minus TI. Now, let me give a few examples and see how we use these two formulas. I have some zinc powder. I add it to a solution of silver nitrate. This is a temperature rise. So they ask me to calculate the delta H for this reaction. So this is a reaction here. So I'm going to call out the first formula, Q equals MC delta T. My M here is the mass of the solution, which is equal to the volume of the solution. So my M here is 50. My C is 4.18. My delta T is 25.4 minus 21.1. So I find my Q first. That's the first thing. Now, zinc powder added to silver nitrate. Most often than not, your solid is the limiting reagent. Because when the solid goes into the solution, your solid will have totally dissolved. But just to be safe, let's prove it. So I'm going to find my number of moles of zinc. I take the mass divided by the AR. I'm going to find my number of moles of silver nitrate. Now, 1 mole of zinc, we have 2 moles of silver nitrate. So if I have this number of moles of zinc, 0.002, I will need about 0.004 moles of silver nitrate. I have more than enough. So therefore, my silver nitrate is in excess. I prove that my zinc is the limiting reagent. So with that, I call my second formula. Delta H is equals to minus Q over my N. I know my Q, I just found out 898.7. My N is the number of moles of my zinc. I put it in, I find my delta H. Now, initially, the delta H that you found is in joules per mole. You divide by 1,000, change it to kilojoules per mole, leave your answer in 3 seconds. In this example, please take note, your mass of zinc is not included. Because when your zinc goes into the solution, as seen from here, your zinc is the limiting reagent. It has been totally used up. So your M here is just the mass of your silver nitrate, that's all. Okay, example number 1. Okay, now let's do the second example. I have 60 cm cube, 1 mole sodium hydroxide, add to 40 cm cube, 1 mole HCl. They ask me to calculate the delta H of this reaction. This is a neutralization reaction. So we're going to focus on water. Now, HCl and sodium hydroxide, their initial temperature is different. For simplicity, we are just going to take the average of these two. So this will be 27.7. So this is my average initial temperature. I call my first formula, Q equals to MC delta T. My M here is the mass of the solution. I have 2 solutions. 60 cm cube sodium hydroxide, 40 cm cube HCl. So my M is 60 plus 40. My C is 4.18. My delta T, I take my TF 33.1 minus my TI. So I calculate my Q first. This is my neutralization reaction. I find my number of moles of HCl, 0.04, my number of moles of sodium hydroxide, 0.06. I find that my HCl is the limiting reagent. So HCl will determine the number of moles of water formed, which is also 0.04. So with that, I call my second formula, delta H is minus Q over my N. In this case, my N is the number of moles of water, because this is a neutralization reaction. I know my Q, I know my N, I plug it in, I'll be able to find my delta H on neutralization is minus 56.4 kilojoules per mole. Okay, so this is the second example. Okay, now let me give the last one. I've methanol burning to heat up a liter of water. So they give you some data here. They ask you to find out what is the combustion value of methanol. Okay, now let's call the first formula Q equals to MC delta T. Now I have two liquids here. One of them is water, one of them is methanol. How do I know what is the M? Very simple. If you have done this experiment right, you just ask yourself, where do you see the thermometer? Where the thermometer is where the M is. Okay, your thermometer is now placed in the water. So your M is the mass of the water. So in this case, it is 200. Your C is 4.18. Your delta T is TF, 39.3 minus by TI. I calculate my Q first. Now, if water is being heated up, your methanol must be the limiting reagent because you're burning up methanol to produce heat. So I'm going to find the mass of methanol used first. I just take the mass of the methanol before and after combustion. I know the mass. I divide by the M out of 32. So this will give me the number of moles of methanol. I call my second formula. Delta H is minus Q over N. I know Q. I know my number of moles of methanol. I put it in. I'll be able to get minus 315 kilojoules per mole. Clear? Okay, so this is your step calculation. Now, the actual value for the combustion of methanol, we burn 1 mole of methanol. Okay, in actual reality, it gives out 726 kilojoules of energy. But in this experimental value, when I burn 1 mole of methanol, right, you only give out 315 kilojoules of energy, which is actually less than half the actual value. Okay, why so? Now, calorimetry has one big issue, which is heat loss to the surrounding. If you look at this setup, when methanol is being burned, you expect all the heat produced to be absorbed by water. However, it is not. When your methanol is burned, a lot of heat is actually lost to the surrounding. Some of the heat can also be absorbed by the copper can. So ultimately, right, the amount of heat absorbed by water is actually very low. As can be seen from the value, right, actually less than half of the heat produced is being absorbed by the water. Okay, so this is the most common reason we give. Can you think of another one? If you can, leave in the comments below. Okay, so this is the first kind of calculation which we call calorimetry. Now, the second kind of calculation I'm going to show you is an indirect method to find enthalpy change. Now, when I say indirect, it means that we cannot measure the TF, the final temperature, and the TI, the initial temperature. So we have to use the indirect method. So with that, let's do a definition first called Hess's law. Now, Hess's law says that for a reaction, the enthalpy change remains the same, regardless of what route you take, provided the initial and the final conditions are the same. So your initial is A, your final is C. From A to C, this is a one step, denoted by delta H1. Or from A to C, my A can go to B first, delta H2. My B then go to C, delta H3. So Hess's law basically just means your clockwise enthalpy equals to the anti-clockwise enthalpy. So delta H1 is equal to delta H2 plus delta H3. So this is Hess's law. So we're going to use Hess's law to construct this cycle called a Born-Haber cycle. Now, Born-Haber cycle is drawn specifically for ionic compound. It can be drawn in an energy cycle manner, which is my personal favorite, or it can be drawn in an energy level diagram manner, depending on your school. Now, I'm going to draw a Born-Haber cycle for you in an energy cycle manner and an energy level diagram. Okay, just let me compare. To draw a Born-Haber cycle, there's a fixed way. You follow this four alphabet, F, A, I, and L. Formation, atomization, ionization, and lattice energy. So using this four alphabet, let's try and construct a Born-Haber cycle, okay, for sodium chloride. Now, let's do it in the energy cycle manner first. Okay, so please look at the screen. So my Born-Haber cycle, I'm going to start off with formation. Okay, so formation means I'm going to form 1 mole of sodium chloride solid from the elements in the standard state, which is sodium solid plus half chlorine gas. So the value is minus 411. So this is my formation. I'm just going to call it F. Okay. After formation comes my atomization. I'm going to atomize sodium and chlorine. Sodium solid will become sodium gaseous atom. The value is plus 107. Chlorine molecule, I'm going to atomize it to chlorine atoms. The value is plus 122. So this is my atomization A. Okay. Right after that, we do ionization. Ionization, there's 2 of them. First up, I'm going to change sodium gas to sodium plus gas. This is what we call the first IE. And the value is plus 494. I'm going to change my Cl atom to Cl minus gas. Now, Cl gets the electron from sodium. As sodium becomes sodium plus, it gives out a mole of electron. That electron will be taken in by Cl gas to become Cl minus gas. So this is what we call our first electron affinity, and the value is minus 349. So collectively, this 2 is what we call ionization. Okay, and lastly, my sodium plus gas plus chloride gas, I go up. This is my L lattice energy. Okay, so this is a Born-Haber cycle in the FAIL manner. So to solve it, I'm just going to write by Hess's law. If you look carefully, F is the only arrow that goes clockwise. Your A, your I, and your L all go anti-clockwise. So F is equal to A plus I plus L. Most often than not, when we draw Born-Haber cycle, it is to calculate the L, the lattice energy. So this is a Born-Haber cycle in an energy cycle manner, which is my favorite. Now, I'm going to show you how to draw a Born-Haber cycle in an energy level diagram manner. Okay, now in an energy level diagram, you have to take note. Endothermic reaction, you point up, arrow. Exothermic reaction, your arrow point down. So there's only 2 kinds of arrow, up and down. There is no left arrow, there is no right arrow, only up and down. So I'm going to draw my axis first. My y-axis, I'm going to call it energy, kilojoules per mole, 0. So same thing, I'm going to start off with my F formation. So sodium solid plus half chlorine gas. The value is minus 411, minus, I point my arrow down. So I'm going to form a mole of sodium chloride, solid. So this is my F formation. Okay. After my F, let's go atomization. I'm going to atomize sodium and chlorine together. Now I can combine them together because they're the same fraction atomization. So I'm going to combine the 2 values together. So this is plus 107 plus 122. Sodium solid becomes sodium gas. Chlorine molecule becomes chlorine atom. So this is my A atomization. I atomize both sodium and chlorine together. Next, let's do the I. Okay, I'm going to change my sodium gas to sodium plus gas. You will give out more electron. Your Cl gaseous atom, you did nothing to it, just bring it up. So this one, my value is plus 494. Recall, this is your first IE. Okay, now this electron will then be taken in by your Cl to become Cl minus. Cl minus, the value is minus 349. So this time round, my arrow must come down. So sodium plus remains. Now chlorine atom become chloride. So this is your minus 349. So this is your EA. So IE, EA, collectively, we call it ionization. Okay. And lastly, my sodium plus gas plus chloride all the way down. This is my lattice energy. This is my F. So this is a Born-Haber cycle in an energy level diagram manner, which is a little bit more complicated because of the up-down arrow. Okay. So this is all I have for you today. I hope you have learned something. If you have any comments, please feel free to leave a comments below the channel, and I'll see you again. Okay, thank you. See you. Bye.